Okay guys, in this video we are going to go into a bit more detail as far as the thermodynamics of phase transitions are concerned. And specifically we're going to be looking at the effect of temperature and pressure. So this first equation reminds us a couple of things. First off, for a single component system, that is a pure substance, the chemical potential is defined as the Gibbs molar energy. So just the Gibbs energy of the system in absolute units of energy divided by the number of moles of system. So that's what this mu is, the chemical potential. The next part of the equation reminds us that a change in the molar Gibbs energy, or the change in the chemical potential, brought about by either or I should say and or a temperature and pressure change, is given by this formula here, where the slope of the chemical potential with respect to temperature is given by minus the molar entropy, and the slope, that is the change I should say in the chemical potential with respect to pressure, is given by the molar volume. So this is something that we've looked at previously. How does the Gibbs energy change with respect to temperature and pressure? The situation is no different here, except for now we're talking about the same quantity, only we're calling it chemical potential. Okay, so this is one of the fundamental equations that we'll be working with in this this topic. And the first bullet point, or the second bullet point here, focuses in on the temperature dependence. And this is a really useful expression to know. Again, how does the chemical potential change when we change the temperature at constant pressure? It's equal to minus the entropy, the molar entropy. And then if you couple that with this fact here, that the molar entropy of a solid is less than the molar entropy of a liquid, which is much, much less than the molar entropy of a gas, it allows you to understand, thermodynamically speaking, how phase transitions work with respect to temperature. And so this is actually a diagram that we've looked at before, but it's well worth looking at again. So here we're plotting the chemical potential versus temperature, and I'll point out one more important rule in chemistry, that is, spontaneous transitions occur in the direction that lowers the chemical potential. So you can think of the system as always trying to find a lower chemical potential. Right? So what we're plotting here, we're plotting the chemical potential of different phases as a function of temperature. So this line right here, it's red at first, and then it changes over to the white line. That is the chemical potential of the solid with respect to temperature. It's being modeled as a straight line, but it's not necessarily a straight line. It would have some curve to it, but a straight line's good enough here. This line right here, which goes from white to red to white again, that's the chemical potential for the liquid phase as a function of temperature. And the reason why the two lines have different slopes is because the chemical potential of the solid is smaller in magnitude than the chemical potential of the liquid. Okay, so going back to this equation, so this is the slope of the chemical potential with respect to temperature. It's always going to be negative because the third law of thermodynamics tells us that entropy is always positive. So the chemical potential will always decrease with temperature, and the steepness of the chemical potential line will depend upon whether you're talking about a solid, a liquid, or gas. Okay? So the reason that the liquid line is steeper than the solid line is because the liquid has a larger molar entropy. And if you look at the line for the gaseous phase, okay, you see it's the steepest of all three because the molar entropy of a gas is much, much larger than that of a liquid. Now, combine that with the rule that the most stable phase will have the lowest chemical potential. Well, at cold temperatures, right, the liquid line is well above the solid line, and the gas line is well above both of those lines. So at low temperatures, the solid is the most stable phase. At a certain temperature, however, the liquid line overtakes the solid line, and we see that in this region, the liquid chemical potential is lower than both the solid and the gas. Okay? And so this is the region where the liquid is most stable with respect to temperature. And then at a certain point, however, the gas line will overtake both the solid and the liquid, and at high temperatures, it's the gas chemical potential that's lower. At these intersections, so where the solid line, where the chemical potential of the solid equals the chemical potential of the liquid, we have solid-liquid equilibrium. This is where the melting point occurs. Over here, where the liquid chemical potential line crosses the line for the gas, we have the liquid in equilibrium with the vapor, and this defines the boiling point. Right? So one of the other facts that we learned about as far as phase transitions were concerned, when you have two phases in equilibrium, the chemical potential is the same in all phases. Let's see, here we're being asked to calculate the change in the chemical potential for liquid water and water vapor as its temperature is raised from 100 degrees Celsius to 101 degrees Celsius. So the change in chemical potential as the temperature is raised. So let's take a look at this expression, and we'll get some use out of it. So we have the differential with respect to the chemical potential. It's equal to minus the molar entropy times dt. And then there's also this plus Vm dp, but we are not considering pressure changes right now. So we'll make the pressure changes 0. And we'll focus on this guy. Okay. So we're going to go ahead and make, since this is a small temperature change, we can go ahead and write this, we can write this approximately as chemical potential at temperature T2 minus chemical potential at temperature T1 will be equal to minus the molar entropy of that phase times T2 minus T1. So if you like, I've just integrated both sides, assuming that the molar entropy doesn't change with temperature very much. And it doesn't, over a small temperature range you can get away with that, but for a larger temperature change you would need to take into account the temperature dependence of the molar entropy. Okay, so this is an approximation. So we want to calculate the difference for both the liquid and for the water vapor. So we'll just run the numbers for the liquid first. So this will be the liquid. We'll plug in minus 86.8 joules per Kelvin, and that's 1 degree Kelvin. So we get minus 86.8 joules. That's the difference in chemical potential when you heat it up by 1 degree. For the vapor, it's the same thing, only we use the minus 195.98 joules per Kelvin. So I guess that should be there. We don't need that. Now let's think about it for a second. So at 100 degrees Celsius, that's the boiling point. So we're here initially, right? The two chemical potentials are the same. But then when you heat it up by 1 degree, what happens? The chemical potential of the vapor drops by a lot more than the chemical potential of the liquid. So as you go from 100 degrees Celsius, where you've got two phases in equilibrium, to 101, the chemical potential of the vapor will be lower. Spontaneously, you expect the liquid to vaporize. Here in this slide, we're looking at the other part of that equation that we had at the beginning. We're focusing on the change in chemical potential with respect to pressure. So here we've got the change in chemical potential with respect to pressure is equal to the molar volume. And we can couple that with the fact that there's not a very large difference between the molar volume of a solid and a molar volume of a liquid. Sometimes the solid has a larger molar volume. For other substances, the liquid has the larger molar volume. Okay, so here we don't know which one's greater necessarily. Typically, for most compounds, the solid does have a smaller molar volume, but not for all. For example, for water, it's the other way around. Water has a larger molar volume than ice has a larger molar volume than liquid water. Both of those, however, these are the condensed phase. These will both have much smaller molar volumes than a gas. Okay, and so that tells you something about this equation. What we'll find when we start looking at some of the diagrams is that the melting point of a substance is not going to be very strongly affected by pressure. And that has to do with the fact that these two molar volumes are about the same between the solid and the liquid. Okay? There's two cases. Either the solid has the lower molar volume, in which case you find that the melting point slightly increases with pressure, or for a substance like water, where the solid actually has the larger molar volume, what you'll find is that the melting point slightly decreases with pressure. So even though the melting point is not strongly affected by water, however, because the gas, the vapor, the molar volume is much, much larger than the condensed phase, what we find is that the sublimation temperature and the vaporization temperature, these are in fact very strongly affected by pressure, and they both increase with increasing pressure. This diagram, there's two parts to it. This illustrates what we're looking at here is at the point, like for example, this point right here. We're looking at, say, high pressures where this line represents the solid's chemical potential and this one represents the liquid's chemical potential. In this case, the molar volume of the liquid is larger than the molar volume of the solid. So this would be for a normal type of substance, one that's not like water. What happens when you decrease the pressure? When you decrease the pressure, if you make the pressure smaller, it's going to cause the chemical potential line to decrease, right? Because molar volume is always positive. So if this number gets smaller, so for example, if the change in pressure is negative, then due to the fact that this is positive means that the change in the chemical potential has to be negative. So when you decrease the pressure, the chemical potentials drop. Okay? Because this is a substance where the molar volume of the liquid is larger than the molar volume of the solid, the liquid line drops by a lot more. So the vertical distance between this blue dotted line and the red dotted line, that change corresponds to the molar volume. And so here the change for the liquid is huge compared to the change for the solid. It may be exaggerated just to make the diagram more clear. But what happens? You see that when you drop the pressure, the freezing point decreases. You could think of it in reverse. You could think about increasing the pressure as well. So if you increase the pressure, then the curves, these two curves here, they jump up, and that causes the freezing point to increase. The new freezing point is at a higher temperature than it was before. You can flip that around. So for example, let's suppose that we're talking about a substance that is like water, where the molar volume of the solid is in fact larger than the molar volume of the liquid. There, when you go from the low pressure to the high pressure, the solid line jumps up by quite a bit, but the liquid line does not jump up by as much. In that case, what you find is that the original melting point, when you increase the pressure, you find that the melting point goes to lower temperatures. Right? So here's the original intersection where you have solid-liquid equilibrium. Then you bump up the pressures, you find that the new intersection is at a lower temperature. Let's see, so recall that the term vapor pressure refers to the pressure of the vapor of a liquid when the liquid and the vapor are in equilibrium. So I usually remember this in terms of a picture. So this is my vapor pressure picture. I've got a sealed container with some liquid in it. The liquid comes into equilibrium with its gaseous, with its gas, and then the partial pressure of that gas is what we call the vapor pressure of the liquid. So here what they're saying, and you can do this for solids as well, right? You can also do it for a little solid sitting at the bottom, right? You've got your solid here. It is in equilibrium with the vapor above it, and then the partial pressure of the vapor above the solid is called the vapor pressure of the solid. Either way. So what's being discussed here in this slide is that, and we previously talked about how vapor pressure depends upon temperature, but vapor pressure of a liquid also depends upon the applied pressure. And so in this slide, what we're expressing is the pressure dependence of the vapor pressure of a solid or a liquid. And if you increase the applied pressure to a liquid or solid, what you find is that the partial pressure of the vapor above that liquid or solid increases. It has this sort of exponential dependence upon the increase in pressure, and then this is the molar volume here of the liquid. We should note that there are limitations to this formula. We're not taking into account the fact that, when you apply a pressure to a liquid, let's suppose you use an inert gas to increase the pressure on a liquid, we're not taking into account the fact that gas might be dissolved in that in that liquid. So here's a diagram showing you how you would increase the pressure on a liquid sample. You could either use a piston that has a porous piston that allows the vapor to pass through but not the liquid. So you could squeeze on the liquid like this and it would let the vapor go above the liquid. Or you could start pumping in some inert gas into the container, I don't know, like argon or helium. The equation that we have here assumes that none of the argon is going to dissolve into the liquid, which is probably not that great of an assumption, but in any case, you get the idea. So here's a little problem dealing with this effect on the vapor pressure. They want us to calculate the percent increase in the vapor pressure of water if the applied pressure is increased by 10 bar. And if I can remember the formula, it was something like P equals P star e to the molar volume of the liquid times delta P, and then I've already forgotten the other part of the equation, RT. I thought that's probably what it was. So here the delta P is 10 bars. We have enough information to calculate the molar volume. This is the original vapor pressure, and this is the final vapor pressure. They want us to calculate the percentage, so they want us to calculate this quantity. So e to the Vm delta P over RT times 100 is what they want. So the molar volume, we can get that by taking the, they give it to us, it's 18.1 cubic centimeters per mole. And that's milliliters, sorry. And so I'm going to convert that to liters, so we'll take that times 10 to the minus 3 liters per cubic centimeter. So there's the molar volume. The change in pressure is 10 bars. And I want to convert that to joules. So I'm going to say that a liter bar, or that there are 100 joules per liter bar. That's the conversion factor between liters and bars and joules. So we've got all of these things being multiplied together, and then we need to divide by, I'll put it over here, R times T, 8.314 joules per mole Kelvin, and that's at 298 Kelvin. And that's going to be the end of the exponential. So we'll run these numbers through our calculator. Guess I'll start over here, 18.1 times 10 to the minus 3. Take that times 10 times 100. Divide by 8.314. Divide by 298. I'm getting something like 7.3 times 10 to the minus 3. Then we'll take the anti-logarithm. I'm getting like 1.007 multiplied by 100. Okay. And so this ratio is 100.7%. So the increase is by 0.7%, right? If we started out at 100%, it increased to by 0.7%. So that's the increase in the vapor pressure. This is probably not a high priority problem, just so you know. The Clapeyron equation is a lot more important. There's a lot more problems dealing with that in the homework. I should suspect. The Clapeyron equation describes the slope of the coexistence curve for any phase transition. And so let me just illustrate, right? We've got our generic phase diagram. Here's its triple point, right? We've got solid, liquid, and gas. This is something that you should be able to do. Write out a generic phase diagram. Okay. Notice that I've drawn this line very steep, whereas these lines, they have more of a curve to them. The critical point will be somewhere out here. Triple point's right there. What the Clapeyron equation does is it describes the slope, that is dp dt, of any of these coexistence curves. And it's really not that hard to derive the Clapeyron equation. In fact, it's kind of a neat derivation, and so I might just go ahead and spend some time talking about it. Along any coexistence curve, we have equilibrium between the different phases. So this works for any of them. Now, when you've got two phases in equilibrium, it means that the chemical potentials of the two phases are the same. And so at every point along here, the two chemical potentials of the liquid and the gas are the same. Along this coexistence curve, the chemical potential of the solid equals that of the liquid. And along this one, it's the solid and the gas. So what we're doing is we're moving along one of these lines where the two chemical potentials are the same. So if there's a change in the chemical potential of the solid as we go from one point to another, there's going to be a correspondingly equal change to that of the liquid. Okay? And that's what this first line here is on the slide. So for any point along the coexistence curve, the change in the chemical potential of the alpha phase, whichever one that is, must be equal to the change in the chemical potential on the beta phase. And if you go back to the first equations that we looked at in this particular presentation, this can be expanded as minus the molar entropy of the alpha phase times dt plus the molar volume times dp. And you can do the same thing for the beta phase on the other side. Beta, that would be dt plus Vm beta dp. And so now what you do is you start rearranging the equation and you solve for dp over dt. So let's bring I'm going to put the volumes on this side. This should be the volume of the alpha phase, and I'm going to put the temperature on this side. So I'm going to have Sm beta minus Sm alpha dp, no, that would be dt, equals Vm beta minus Vm alpha dp. So I moved the temperature terms over here, I moved the volume terms over there. And now what we can do is solve for dp over dt, the slope. And that's going to be equal to delta Sm over delta Vm. Like that. So that's where the first part of the Clapeyron equation comes from. Think back to our definition of the Gibbs free energy. G equals H minus Ts. For isothermal, you can write, for isothermal and 1 mole, you can write this. That's a minus sign right there. And furthermore, at equilibrium, the change in the Gibbs energy between the two phases is 0, right? The two phases have the same molar Gibbs energy, so this equals 0. And so you can solve for delta S will be equal to delta H over T. Substitute this in, and you get that result there. Okay, and so that's the second part of the Clapeyron equation. You can use either one. And the reason there's a TRS subscript in the Clapeyron equation is because these are the, I probably should have put that M there, these are phase transition, changes in for corresponding to a phase transition. We can take the Clapeyron equation and we can push it a little farther as long as we're willing to make some approximations. So one thing we can do is make the approximation that the enthalpy change doesn't depend upon temperature and pressure. It actually does, but we can assume that if we're dealing with a small enough temperature or pressure change that that it's a constant. And let me just show you where they come from. So we have dp over dt equals delta H. Let's do this for fusion. T fusion. And then we would have delta V for fusion. So what we can do is rearrange this equation, and we'll write dp equals diffusion H over delta fusion of the volume, and then we'll have dt over, we'll just call it T for now. So this T fusion is the same as that one. Well, what we can, if we make the assumption that the enthalpy of fusion and the volume change of fusion are constant for small changes in temperature, what we can do is integrate both sides of the equation. And so we're going to wind up getting P minus, here we're going to be integrating from P star to P, and we'll integrate this from T star to T. So we'll get P minus P star and this will be natural log of T over T star. Okay, and so this is an approximation that we can use to calculate the new, this would be the pressure, a pressure point along the solid-liquid equilibrium curve at one temperature given the temperature and pressure at a different point. So this equation relates 2 points along the solid-liquid equilibrium curve. So just going back to the diagram. This equation would approximately relate any 2 points along this curve. We can do the same thing for gases. It's a little bit different. For gases, we cannot assume, so we can do this for either the sublimation curve or for the vaporization curve. But you can no longer make the assumption that the change in the volume for a phase transition involving a gas is zero. That wouldn't be very accurate at all. And so we'll go back to the dP over dt equals delta H. I guess I'm doing TRS this time. So this would be for either sublimation or for vaporization. And what we are going to assume is that when you undergo that phase transition volume, it's going to be the difference, the change in the volume will be the volume of the gas minus the volume of whatever the condensed phase is. And that this is so much larger than that one that this is approximately the molar volume of the gas. And so we can write this equation like so. Now the molar volume of the gas is going to be RT over P. So we can make that substitution. That's going to give us RT squared over P. And now we're going to do a little bit of rearranging. So we're going to put the pressures on one side and the temperatures on the other. This is going to give us dP over P equals the transition enthalpy over RT squared dt. Okay, and so now we'll integrate this from P star to P. We'll integrate this side from T star to T. We're going to get natural log of P over P star on this side, and we're going to wind up with a negative enthalpy of transition divided by R, and it's going to be 1 minus T, 1 over T minus 1 over T star. So this is called the Clausius-Clapeyron equation right here. And this is valid for both sublimation and for vaporization. So going back to the diagram, this curve relates 2 points that are along either the sublimation curve, in which case you would use the enthalpy of sublimation, or it relates points along the vaporization curve, and you would use the enthalpy of vaporization in that equation. Okay, so that's the Clausius-Clapeyron equation. Let's see. Calculate the effect on the chemical potentials of ice and water of increasing the pressure from 1 bar to 2 bars at 0 degrees Celsius. The mass density of ice is 0.917 grams per cubic centimeter, and that of liquid water is 0.999 grams per cubic centimeter. So we've got the change in chemical potential is equal to minus Sm dt plus Vm dP. Temperature's constant, pressure changes. Now, solids and liquids, okay, ice and liquid water, their molar volume does not change very much with pressure. So we're going to make the assumption that the molar volume is a constant as you go from 1 bar to 2 bars. So we can integrate both sides of the equation. We're going to get our difference in chemical potential. I'll just call it mu2 minus mu1, and that's what they want us to calculate, the difference. That's going to be equal to the molar volume of the substance times the difference in pressure. From here, you need to do 2 calculations. You would do a calculation for ice, and you do a calculation for liquid water. I'm just going to set up one of these calculations. let's do the let's do the ice. Okay, so we have the mass density of ice. What are we going to do there? Well, we need the molar volume. So we want volume in the numerator, and we want number of moles in the denominator. So what we're going to do is we're going to take the molar mass of the substance, 18.02 for water, that's grams per mole, and then we'll divide by the mass density, 0.917 grams per cubic centimeter. This is going to give us centimeters per mole, and that's molar volume. We want to convert that to probably to liters, and so we'll do 10 to the minus 3 liters per cubic centimeter. That's going to be our molar volume. And then we'll put the pressure difference in bars. Okay, so that's 2 bars minus 1 bar, so 1 bar. And now we would typically want to report the chemical potential in units of energy. So liters bars, there are 100 joules per liter bar. Okay, and that's going to give us the energy that we want. This is a fairly straightforward calculation, so I won't bother with the numbers here. I'll just let you calculate those. And then you would repeat this problem using the mass density for liquid water. Let's see. I think this diagram is meant to help explain, I think I've basically already shown the content of this diagram. It's meant to explain what we mean by the dp dt, the slope along the curve. So we've essentially already covered that.